Hello, everyone. Welcome to this keynote about storage in OpenNebula. We're going to talk about how OpenNebula handles the different storage technologies that is available on the open source marketplace. And in this session, it's going to be me from OpenNebula first talking about this, and then we'll have Yusuf from LINBIT showcasing one of these integrations with OpenNebula. So when we have the purpose of deploying OpenNebula is to deploy virtual machines for the end user in order to run dedicated workloads. When creating a virtual machine, there's usually options to choose from regarding the virtual machine storage. You can select options that uh, allow increase I/O performance, or there are also another options in order to allow better reliability by having storage over the network and whatnot. So how do we allow the user to select which storage technology they want to use? So first we have this, we provide this concept called data stores. These data stores are like any sort of medium or entity that can hold on to an array of images. We have distinct types of data stores for each with its dedicated purpose. So first we have the image data store. On this data store, you basically upload images and will act as an image repository source. When you create a virtual machine, the image is pulled from that data store, and then it is transferred to the system data store. This other data store represents the storage that the virtualization node is currently using to run the VM workload. Then we also have another data store, which is the file data store. It's similar to the image one, but instead of acting as an image repository, when I mean image repository, I mean a VM disk based repository. So you create virtual machines from the VM disk, and with the file data store, you can pass files directly from the image data from the file data store to the system data store. Then we also have a newish kind of data store that we introduced a while ago. Is the backup data store. In this case, the only purpose of this one is to hold on to backup type images, and then you can restore these images onto an image data store to then deploy another VM. So next, let's take a look at what kind of images can we deal with in OpenNebula and what the purpose of each is. So we have the basic image type, the operating system image. You define this on a VM template, and then you can create a virtual machine based on the operating system that you define. This is basically the root file system that will be used to run the operating system. Then complementary to that, we have this data block image. This is just a blob of data that you can use to separate storage from the main OS file system. You don't have to do this. You can use a bigger operating file system image, but it's in case you need like dedicated storage for a specific purpose within your application, you can use this data block. Then we also have the CD-ROM images. These will be ISOs that will be passed to the VM on the CD-ROM device, and then you can mount it inside the VM, read only, of course. You can use it for purposes like the Windows VirtIO drivers, or even the contextualization feature that we provide. We use this type of image. Then, as I mentioned before, there's also a backup type of image. This image contains the storage of a running of a VM that was backed up, plus the VM metadata that you restore, and then the result of that restore operation is storage of a VM and a VM template that will reference that storage in order to create a VM whenever that VM template is instantiated. Then we also have some more niche type images. The use cases of these are particularly interesting when using like micro VMs or Linux containers. We have the kernels. The micro VM images do not have a kernel, and you can pass directly the kernel that you want to use when putting that VM. And you also have like run these type files that you can use during the boot process on the init RD phase. And lastly, we have file type images. You can use these to uh, provide custom scripts for your VMs or custom information. These files will be passed through the VM, and the operating system will be available to use them however you see fit. So we have also another type of storage abstraction. In this case, is the marketplaces. These are higher level storage abstractions. Instead of being an image repository, is more so suited as a application catalog repository. We provide a public marketplace where you can. This is if you enter it, you'll see it. We have several type of Linux distributions, kernel images as well, multi VM application that contain like multiple VM templates plus multiple storage for each of those VM templates. And in what these do is they provide an application catalog that then you can pull to your local image data store. And you can also export your, if you have like custom applications, you can also export to a marketplace. It's not only the public marketplace, but we also have the ability to create private marketplaces, and you can also like create your own specific type of public marketplaces. So now that we have defined what storage entities that OpenNebula provides, let's take a look at a workflow that showcases the interaction between these different type of storages. So this is not a specific workflow. Like this is, and it doesn't have to be always like this. It's just a means to showcase the interaction between all of the image data stores and or all the different type of data stores. So first, we have a bunch of applications available in the marketplace. The user then imports any of those applications onto your local cloud deployment. The application may or may not contain multiple image definitions, file definitions, but what you do is you import those onto your image data store or your file data store. Then after a while, those applications or those images of the applications will be marked as a ready state. That means that you can now create virtual machines based on the metadata that you just downloaded and the storage that you just created on your image data store. Then a transfer process will begin from the image and file data store to the system data store. Once this transfer process is done, the KVM host will then run the virtual machine. These virtual machines, then you can back them up, and a backup process will be started, and this will be stored on the result of that backup process. If it succeeds, will be stored on the backup data store. Then you can optionally restore this backup onto your image data store, and this basically completes the cycle again. The result of the backup will be an image plus its VM metadata that you can use to then instantiate that template again. And this is how it all kind of fits together. So the thing we do in OpenNebula is like we provide the ability to control how these processes are executed. We provide something called drivers that you can use to bind the mapping of this process to a specific type of technology. We provide like 4 distinct set of drivers. One for data store operations. These are like the operations that run within the same data store, like for example, creating an image, cloning an image, extending it, like all within the same data store. This is the data store driver. And then we have the transfer process. We have a dedicated driver for that. The process of moving an image from an image data store to the system data store. This could be picked a lot. Like you can have a specific storage technology, like for example LVM. We provide you with the ability to use either a shared storage to have like images easily available as an NFS mount point, or you can also use like local transfer with SSH and LVM. So it provides you the ability to optimize or change the behavior of certain type of technology in a specific step while still using the same technology. Basically, you have like two ways or multiple ways to use the same technology. Then we also have the backup driver. This is very simple. It basically allows you to write or customize the backup operation process and the restore operation process. And then we also provide the marketplace driver. This allow you to create public and private marketplaces. We provide an official marketplace, but using this same like driver approach, we also created more public marketplaces, which are they are not integrations done by us, but they are not a marketplace that we provide. But we do still have provided for the end user as a public marketplace that is available. So with these drivers, you can take a look at each of the technologies that we implement. For example, for data store and transfer operations, we have this like NFS or like NAS driver. Then we also have local storage, which was known as the SSH driver. There's also a variant of that with one store that uses the transfer driver to optimize different like to enable a sort of cache approach and to minimize the transfer period. Then we also have the Ceph driver, and rsync is an example of the backup driver. We also have restic, and you can take a look at how do these drivers work and how to development on the links that I showcased on this presentation. So now we will have Yusuf from LINBIT to showcase how these drivers approach and how this like modularity is used by LINBIT to provide the use of their storage technology within OpenNebula. That's it. Let's welcome Yusuf.
Thank you. Hello everyone, my name is Yusuf Yildiz. I am a solutions architect at LINBIT. Welcome to this presentation where we will together explore how LINBIT SDS software-defined storage seamlessly integrates with the OpenNebula ecosystem. Before we start, I would like to shortly explain who we are. LINBIT is a 20 years old company who became a block storage pioneer in the open source world. We are the developers of DRBD, the famous DRBD distributed replicated block device, which is included in the Linux kernel since 2009, and also the software-defined storage LINSTOR. The LINSTOR is one of the open source software-defined storage in the market. As far as I know, there is only two. We provide 7/24 support to all of our customers around the globe with 2 offices in 2 different continents. Our headquarters is in Austria, Vienna, and our USA office in Portland, Oregon. Our team consists of highly experienced Linux specialists, and our developers are placed in both LINBIT headquarters and also LINBIT USA. We have exclusive partners also all around the globe. We have SIOS in Japan. We have different partners in Africa, Turkey, and many other countries or areas. At LINBIT, our core mission is to empower you to take control of your storage. This sounds like a marketing sentence, but it's not. It's an actual thing. So our solutions are designed from the ground up to prioritize your data protection, and it ensures your critical services remain online. We have a great track record of 24 years with no single SLA lost, and deliver the performance that you need. And it doesn't stop there, because we believe in breaking free from the vendor lock-in, whether it's software or hardware. It's really, really crucial. You already know that There are many debates ongoing in the market for especially the virtualization software. So LINBIT will try to help you get out of that situation. With LINBIT, you actually build an infrastructure that is truly yours, one that adapts to your needs, not the way around. All right, let's dive into the LINBIT SDS. At its core, it transforms the ordinary shelf servers into a resilient distributed storage for OpenNebula. You can think of it as building a virtual storage layer, far more robust and flexible than traditional storage arrays. And this storage becomes the foundation of your OpenNebula virtual machines, and providing them a volume that are not only highly available, also incredibly easy to manage and scale as your needs evolve. LINBIT, when I say LINBIT SDS, there are too many tools involved under this name, including the open source DRPD and the LinStore, and there are LINBIT GUI, LINBIT Gateway, and so on and so on. But at its core, LINBIT consists of two components, the controller and the satellite. As the name suggests, the controller manages the satellites manages the hosts, or the hyperconverged hosts, or the storage nodes. It doesn't matter if you have a hyperconverged environment or disaggregated storage environment, you have to install the LinStore satellite service to your nodes. And as you can see in the picture, the LinStore satellite and the controller is completely separated from DRPD, and there's a reason for that. Because DRPD is handling the data lane. So when you want to have a replicated VM disk, the engine who does it, it's DRPD. And it's completely separated from the LinStore. That means if you would like to remove LinStore completely from your system, I'm not talking about a maintenance or something. Let's say you want to remove it. It doesn't matter. Your VMs will keep on running. Even if you remove the DRPD from your kernel, you can still reach the data. That's the core power of LINBIT SDS. So whatever we used, whatever we installed in your system, it can be removable while everything is running, or you can reach your data at any given time. So the controller and the data plane completely separated to help you to get over operational issues such as upgrading your LinStore controller or satellites or services and so on. Obviously, the LinStore controller talks with the OpenNebula all the time to get the requests for the VM disks. For example, if the OpenNebula asks for two-way replicated storage for one of the VMs, the LinStore controller checks the satellites, hands over these requests to the satellites. Satellites creates the relevant drives, block devices within the hosts, and then hands over these drives to the hypervisor layer. And these block devices are always in sync. Either it's synchronous mode or asynchronous mode, you choose. All right, so what does the OpenNebula storage stack looks like with LINBIT SDS? There are three options, obviously. The hyperconverged approach, the disaggregated approach, or mixed. I also saw some of the customers are using mixed approach. And in this example, what you see here is a hyperconverged infrastructure. It's pretty easy. I bet you already know how it works. So a VM has a local drive, which is replicated with another drive in another host. When a host fail or disk fail or network fail, that VM moves into another hypervisor. It remotely reads to the other DRPD device, which has already been replicated before synchronously. Not a single data is lost. And the VM will keep on running on DRPD's diskless mode. Then it becomes a disk full after X minute of time, you decide. If you decide that host failed, gone forever, you can create another replica automatically within LinStore with a given time. Or you can recover that host, the VM gets its drive back, and then you can move the VM back to the hypervisor if you like. Obviously, the other approach is the disaggregated storage. So what you have here is storage nodes are separated from the compute nodes, and all of the VMs are in diskless mode. Diskless mode means the drives of the DRBD, the replicated drives, are shown in the compute nodes with the help of LINBIT, the LINSTOR satellite. And the LINSTOR satellite creates these DRBDs diskless drives within those compute nodes, and they are reading and writing locally, but it's actually in the remote storage nodes. If you lost that compute node for some reason, VMs fail over, nothing happens, VMs just keep on running because you already have that virtual DRBD device within that compute node as well. So the VM will think that I already have a drive here that I need. It will just continue working without any issue. Another thing might happen is you lost your storage node, obviously. If that happens, don't be afraid, because every disk is two-way replicated minimum in the LINSTOR environment. So the VMs will still keep reaching its data 100%. There is no rebuilding, nothing involved. Once you once you introduce another storage node within the system to fix this mess, or to add more capacity, then obviously LINSTOR will create more replicas. I can talk about this kind of setups in hours, but obviously the time won't be enough for that. So if you are looking for an actual demo, we have a great YouTube video in our channel. My fellow solutions architect, Matt, recorded this, so please check it out, the OpenNebula hyperconverged storage using LIMIT-STS demo. And we have a great state-of-art user guide in our website, open, freely available also. If you want to try and test LIMIT-STS with OpenNebula, please check that out. Every step is included, how you will install this free software into your system. And if that's not enough, please reach me out from my email. I'm open to your any technical questions, so please reach me out. I will try to help you as much as I can. And thank you for listening. Thank you for joining the OpenNebula Con 2024. And now I'm open for the questions and so on. Thank you so much.